100 kilohertz. Now, so this is the interesting part about this, is that your input power requirements, let's see here. So this one is about 120, sorry. So we have 120 watts here, and then this guy is about about 40 watts. About 35 watts. So it's less than where you had only high side PWM or high or low side PWM. So it's definitely less, because now you are taking the diodes out of the picture. Now it's more like a synchronous rectification. Diodes are not as much being used for reverse recovery. Reverse recovery is reduced. So as a result, your ripple requirements go down. And we can see that other components also not that bad. They're well behaved. So from an input standpoint, and we can look at the input current. Let's say, let's look at IN. That's the input current. And let's see if we can zoom in a little bit. So that's how it looks like at and we can do an FFT on this as well, and we can see we have a DC component, which is so if I do FFT on this, actually it doesn't look too bad. Maybe I can expand it. Let's see. 5 kilohertz. Actually, it doesn't look too bad in terms of FFT. Pardon me?
Harmonics are less.
Yes, and I think you have, so this is your rotational frequency here. And then if I look at this is not your rotational frequency. This is a almost 300 hertz. You have 300 hertz. Let me see what the rotational frequency was on this one. Oh, so 100 hertz. So this is your third harmonic of the. So here the frequency is 100 hertz, and this is almost your third harmonic. I wonder why the third harmonic is coming here. Okay, that's what you have it. All right. Any questions on this one? All right.
What is the efficiency of the system?
I think the efficiency here is, I'm afraid to plot. It looks pretty poor because we have a very large resistance.
And first switching is there both the sides.
Yeah, yeah. So actually you can see it. It's 56 watts output, and input is 121 watts. So you're less than. Yeah, I think this system you need to look at, see why there is. But it's mainly I presume you have 181 milliohm of resistance. So if I do 25 times 0.2, that's 5 watts. So you have almost 15 watts of losses in the winding resistance. Yeah. So 15 watts of, and then we'll have to look at the switching losses and all that stuff.
So efficiency means the losses in the inverter.
Inverter plus the motor. So this is all, everything included.
Show the power waveform you plotted earlier.
Yes, which one? Input or output? Output. So this is the output here.
This is output of the inverter output for the
Or just the inverter output? Oh, that'll be
you already plotted.
I have the output powers. You are really looking at 90% efficiency. You know, at the normal operating points.
Because even earlier the efficiencies were somewhat lower.
Yeah. I think, see, the motor model which we have taken really runs more at milliamps. You know, so we're pushing in that motor model. We're pushing 1 or 2 or 3 or 4 amps.
Which one is the reference you have taken? Where is this used?
This is BN23. This is actually a 2 or 3 Newton meter motor. So we're pushing, in terms of the model, it's fine, but really, I think we're pushing a whole lot more current than we need to. What we need is one component we could actually use in real practice. But yeah, actually, that motor is high-speed motor with the current draw, which is more in milliamps of range than in amps. So yes, this
Where is this BN23 used? Right, sir?
it's used. This is power tools.
But in power use, milliamp is sort of like
Good question. Milliamps out of the milliamps is more than sufficient. Why it couldn't be sufficient?
power tools for what?
Power tools could be for drilling, small drills, portable drills, for screwdrivers, things of that nature.
Because you get them, nowadays you get those screwdrivers operated on batteries.
Right.
That is why that power is this. So it's not battery operated. Very high torque.
You could also use these motors where, you know, install it as a part of a process in the factory. You know, just moving very small things or screws on a belt or something of that sort. Okay, so we have, I think, let's see. So we have shown you the all-channel PWM, and let me quickly cover the large signal model. Now here the goal is to be able to eliminate the inverter altogether, and so that we can do a longer time simulation for a longer time, and get. This is important when you're trying to optimize your phase advance or your inverter parameters, because they're based on the motor performance. So this is more for characterizing the motor. So what we have done here is this block right here. Generates, now this is basically one leg of the inverter, A, B, C. So the max duty cycle PWM signal, we have eliminated the PWM, and so the maximum, the limiter, output of the limiter is fed to this block here. And this block essentially generates voltage as follows. Let me just write down on the board. So it's let's see. So you have, this is your duty cycle, which goes from 0 to 1, and your voltage output goes like this. So at 0.5, voltage is 0, and at 1 it is 18 volts if you have a 36 volt system. At 0 it is minus 18 volts. Okay? So that's exactly what we have done, is replace the inverter with just a behavior analog ABM block. Okay, so it's two times the duty cycle minus 1, right, times the input voltage divided by 2. That's the block we have. So when your duty cycle is 1, it is 18 volts. When duty cycle is 0.5, it is 0, and the duty cycle is 0, it's minus 18 volts. So with that, now this also allows you to make sure that when you are simulating the system, how much of the effect is because of the inverter. If your inverter is not optimized, is it having any effect on the performance of your drive? So this way you eliminate the inverter, you have basically replaced it with an ABM, analog behavior model. Everything else remains the same. You're able to use this. Now this would be easy to incorporate into the speed loop also. And you could now use this system to do body plot and also to choose the correct values of PI. Everything else remains the same. Use the same KP, KI. And what we have done here, all over the place. Let's try that. So here, in this case, voltage has become square, right? We have a square voltage, and then we have a reference, which is, the red is the reference, which is the trapezoidal. All right, so this is how the current looks like. We have got some interesting gashes here. So inverter is out of the picture, so you can basically say this is not contributed by switching, and this is not contributed by diodes. This is essentially a circuit behavior the way it is right now. Okay. And you have got this is the FFT on the IL1, which is the winding current. And we'll get this. We'll see what's happening here in a minute. And these are all three current waveforms. They look horrible. Not really very nice waveforms in terms of. And this is your output power. The output. All right. So let's see if we can go to the demo. No PWM large signal model. Okay. So this is number 5. Number 5. Let's see if this is faster. Alright, so let's look at the circuit. So here, the inverter is gone. The inverter inverter is replaced by these three blocks. We have the duty cycle in here, and duty cycle is limited, and then we generate voltages A, B, and C. And then we still have current sensors here, phase current sensors, and we have added some resistors and currents to smooth out the feedback. And it's almost 100 microseconds of delay in the feedback. So, and everything else, let's see here. Now we have added the parameter. So if you look at this here, TRV and TFV. And TRV, TFV are the new parameters. And let's just look at the voltage here. So now TRV and TFV are 10 microseconds. So you have about a fast square voltage. Let's run it. This is without any PWM, right? So you have got these wiggles. I think KP and KI can be optimized further. Let's see what the value is of KP and KI. Here we have got KP 100 and KI 50. In this model, you could run Bode plot, and then you could easily compensate the system. And then I think since we are running low on time, the last one demo I wanted to show you was where we eliminate the slopes altogether. So when you eliminate the slopes, then of course the current waveforms become much nicer. So I'll show you that part. This is how the voltage and the currents are. And so we eliminate the slopes, so your current waveforms become quite nice, as you can see. And we have plotted some harmonics, which I think you'll be able to plot. You can't really see much, but that's not really important. Let me move ahead. And this is the output power. You have a better power when you don't have no slopes. You know, you have power output increases slightly, almost. I think we were 56 watts, so it goes up to 62 watts. So, all right, and I will not do this demonstration here of the large signal with no slope since we are out of time, but it's pretty much that we have eliminated the slopes and ran the demonstration again. So I'm going to close this demonstration here. And we're going to go to AC inverters, which would be short because a lot of material we followed here is applicable here also. So three-phase inverters. All right. I want to get to induction motor drives before we close. Let's start with induction motor drives, which we intend to spend some time on it. Okay, so we have, we'll do a quick review of sinusoidal inverter. This is really, we were talking about DC drives, and here, we're going to again use the three-phase bridge, and we're just going to have sinusoidal generated duty cycle. And we'll talk about amplitude modulation ratio, frequency modulation ratio, and harmonics, over modulation, and square wave inverters. We have 4 demonstrations here, and this is where you're using these inverters to run AC motors, especially induction motors, right? So we will talk about harmonics and amplitude modulation ratio and so on and so forth. Okay, so the exact same inverter we're using as we have used before. We like these components, so we continue to reuse them. And we have increased the bus voltage here quite a bit. And we have also changed, we use the same PWM generator. So we just feed in the duty cycle and out come the PWM pulses. Exactly the same circuit as we have used before. Now this is the concept I was just talking about. Is this is how we generate the duty cycle. So this here essentially is to illustrate the concept. When this switch is closed, you have VDC across here, and then this switch is closed, you have reverse VDC here. And if you plot essentially with respect to duty cycle, you get minus VDC by 2, plus VDC by 2. D varies from 0 to 1. And then you can also plot, let's see here, so you can also plot here the motor voltage. So the D goes on the y-axis and VM goes on the x-axis. So duty cycle still remains 0 to 1, but you have minus VDC 2. So these are the two equations we have. Motor voltage across the motor is given by this equation. The duty cycle is given by this equation. So using these as the basis, we generate three control voltages. VA control, VB control, VC control. They're all 120 degrees apart. And then we essentially introduce amplitude modulation ratio, which basically is this term. So essentially, the VA control voltage becomes amplitude modulation ratio by 2 times sine of that. And then you have a half here to normalize all of them between 0 to 1. And here you have, now this is PWM all the time, because you're using sinusoidal pulse width modulation, so all switches are getting PWM all the time. And when this voltage here, so this is the A top, so when this voltage here is above the triangle voltage, your top switch is on, and when it is below the triangle, your bottom switch is on. And so you have got gate